Hey everyone, welcome back to Real Analysis 1. This will be lecture 15 of the course. And in this section, we want to explore a finer detail of continuity, and that is the concept of uniform continuity. So let's go ahead and jump into it. And we'll call this section 4.3 uniform continuity. And let's recall what we said about continuity. So we saw, what was our definition of continuity previously? We said that given a function f from e to r, f is continuous on e. F is continuous on e if, well, for all p in E, given any epsilon greater than 0, there exists a delta greater than 0 such that we said that f of x minus f of p is less than epsilon for all x in the delta neighborhood of p. Okay. That was the definition we gave in the of continuity from our previous lecture. Now, if you think about this, and in practice we saw several examples, in general, when you're given an epsilon, how you choose the delta depends on a few things. So in general, given epsilon, the choice, we'll say the choice of delta depends on a few things. Now, the first thing is the epsilon, right? So depending on which epsilon you give me, I have to pick potentially a different delta, right? Frequently we see that, in fact, our choice of delta is based on epsilon, right? You give me an epsilon, I use that to calculate my delta frequently, most of the time, pretty much all the time, right? So obviously epsilon, your choice of delta depends on epsilon, right? Another thing it depends on is the function, right? So if it's an x squared, f equals x squared, or if it's f equals square root of x, or if it's f equals sine of x, or some rational function, whatever the function happens to be, that's going to influence my choice of delta also, right? So epsilon matters, the function f matters. And then thirdly, we frequently see that the point in question matters, right? So if we're trying to test the continuity of the point P, very often the point P that you're interested in is going to influence the choice of delta. Okay, and so this is kind of, so these three things very often come into play when trying to determine what an appropriate delta is given an epsilon. So epsilon matters, the function matters, and the point matters. Now, I will say that most of the time, epsilon and the function will matter. But there are examples where the point P doesn't matter, right? In some cases, the point P the choice of delta is independent of P, right? And so in some cases, the choice of delta is independent of the specific point you're looking at. Okay. And it's these cases that we are interested in these sections, right? And so here we are now in a place where we can define what do we mean by uniform continuity. Okay. So definition, let's let E be a subset of real numbers and f a function from E to R. Then we say the function f is uniformly continuous on E if given epsilon greater than 0, there exists a delta greater than 0 such that f of x minus f of y is less than epsilon for all x, y in E with x minus y less than delta. Okay, so let's think. The key point here, let's rehash this. So E is a function or f is a function from E to R. F is uniformly continuous on E if, given some epsilon greater than 0, I can find a delta such that x and y evaluated at f are within epsilon for all x and y in E, whenever x and y are less than this delta. So the key point is that delta must work for all x, y in E, and it's in no way dependent upon the specific point under consideration. Okay, so it's in no way dependent upon the specific point under consideration. Now, if you look up here at our definition of regular continuity, x has to be within a delta neighborhood of P specifically. Down here, x and y just have to be within delta of one another, and the function will be within epsilon, right? And this is the same delta for every x, y in the domain set E, right? So the key point is that delta must work for all x, y, and it's in no way dependent on the specific point under consideration. So basically, one delta, given an epsilon greater than 0, I can go find a single delta that works for every point in the domain. Okay, and when that's possible, when you can do that, you have a function that is called uniformly continuous. It's not always possible. Okay, let's see some examples. Let's try to draw this out a little better. The first example will be a nice familiar one. Okay, let's think about f of x equals x squared. And let's let this function be defined on E, and we'll say a bounded subset of real numbers. All right. So the key here in this example is that x squared is the function here, f equals x squared, is defined on a subset of real numbers, a bounded subset. So it could be, just think of it like an interval, but with some kind of an upper and lower bound. Okay, so we're not going to let f be defined on the entire real number line in this example. Okay. Now let's show that this is uniformly continuous. F, so defined, is uniformly continuous. Okay, and so here's how you can demonstrate this, and here's how a lot of these work. This is a good example to start with. Since E is bounded, right? E is bounded, it's bounded, the domain is bounded. Since E is bounded, there's going to exist some positive number C such that the absolute value of x is less than or equal to C for all x in E. That just means, your domain function is bounded, right? If the interval under consideration is negative 1 million to positive 1 million, then this C could be 1,000,001, for example. Okay, simple, right? Okay, so E is bounded. There exists some C and some positive number C such that the absolute value of x is less than or equal to C for all x in E. Okay. So then, if x and y are in E, what can we say? Well, then f of x minus f of y is equal to, well, the function is x squared, so this is just x squared minus y squared. And we know that that is equal to x plus y, absolute value times x minus y, like so. Right? And we know that that's less than or equal to the absolute value of x plus the absolute value of y times x minus y. Right? So just kind of breaking this first one apart, and that's where the inequality comes in. Okay. And this, well, x is less than or equal to c, and y is also less than or equal to c. And so this piece of it here is less than 2 times c. Okay, so we'll say less than or equal to 2 times whatever this c happens to be times x minus y. Okay, right? Remember, so this is, keep in mind, this is just because of the fact that the domain is bounded, x has to be less than c, and also y has to be less than 2 times c. Okay, so what can we do? We can say at this point, let's let epsilon greater than 0 be given. And we can take delta equal to epsilon over 2 times c. Okay, so then if x, y are in E with x minus y less than delta, then you can see where we're going. F of x minus f of y is less than or equal to 2 times c times quantity x minus y, absolute value, which is, this piece here is less than delta by assumption. 2 times c is less than delta, and so this is equal to 2 times c times epsilon over 2c, and of course that's equal to epsilon. Okay, and so x and y, so long as they're within delta of one another, it doesn't matter what they are, as long as they're within delta of one another, then the function is within epsilon. Okay, and so this is an example of a uniformly continuous function. Okay. Now it turns out this is false. This is not a uniformly continuous function if we let E be the unbounded real interval. Let's take a look at an example of a function that is not uniformly continuous. Let's say this one, f of x equals 1 over x on x in 0 to infinity is not uniformly continuous. So let's assume, so to show this, we can assume that it is uniformly continuous and derive a contradiction. Let's do that. Okay, so let's assume the reverse. Okay, and let's let an epsilon equal to 1 be given. Okay, so you should, for any epsilon greater than 0, you should be able to define, if it is uniformly continuous, you should be able to find some delta that works everywhere for any epsilon, right? Here's an epsilon where we're going to find that it doesn't work. Okay, so let epsilon equal to 1. Then there exists delta greater than 0 such that f of x minus f of y, which is equal to 1 over x minus 1 over y, is less than 1 for all x, y in 0 to infinity. Okay, well, with, of course, x minus y less than delta. Okay. So this is just what would follow, right? If f of x equals 1 over x is uniformly continuous on 0 to infinity, then this would have to be true. Given an epsilon equal to 1, there must be some delta, right? And so what we can do is we can derive a contradiction. Let's choose n naught, natural number, such that n naught, 1 over n naught, is less than delta. That can always be done. No matter what delta you give me, I can always do this, right? And then we could say, and for n in the natural numbers, we can set x sub n equal to 1 over n, right? Then, for all n greater than or equal to this n naught, what would we have? We would have x sub n minus x sub n plus 1, right? So 2 consecutive is equal to 1 over n minus 1 over n plus 1. Now this is going to be less than 1 over n, right? Right, because I'm just saying 1 over n, I'm going to subtract off a positive quantity, so it'll be less than, right? And so this would be less than 1 over n, which is less than delta. But here's the problem. F of x of n minus f of x of n plus 1, absolute value, this would just be equal to n minus n plus 1, which is equal to 1. Right? And so this contradicts the assumption. This implies a contradiction because f of x of n minus f of x of n plus 1 needs to be less than 1 for all x, y with x and y within delta, right? So obviously we have an x and y within delta, right? You see right here, x and y are within delta, but f of x of n minus f of x of n plus 1 is equal to 1, right? It's not less than 1. Our epsilon is 1, right? So we have a problem here. Okay, and so for this particular function on this particular domain, it's possible to find an epsilon such that there does not exist a single delta that works for all x and y. I've just found a counterexample, right? I've given, working from a general delta, I can find a counterexample. Okay. So it turns out that this function is uniformly continuous if we adjust the interval. Okay, so this function is uniformly continuous on a to infinity. You just have to get rid of that 0. This is always when a is greater than 0. Okay, and we can prove this one. Right, we can prove this one. So let's let x and y be two values in this interval a to infinity. Then f of x minus f of y is equal to 1 over x minus 1 over y, which we know is, we kind of rearrange this a little bit, you get y minus x over xy, like this, right? And this is going to be less than or equal to 1 over a squared times x minus y, right? So because this has, we have this nice bound, right, of a, we can sort of set this up. So then, given epsilon greater than 0, we can choose delta greater than 0. And there's a range that we could choose. We could choose delta greater than 0 such that delta is, as long as it's less than a squared over epsilon, right? Then when x and y are within delta of one another, for this particular example, we have f of x minus f of y is less than or equal to 1 over a squared x minus y, which would be less than 1 over a squared delta, which is less than epsilon, right? So you can pick a specific delta if you want, but as long as it's less than a squared over epsilon and obviously greater than 0, you get this, right? Which kind of shows you that indeed 1 over x is uniformly continuous on any interval a to infinity, so long as a is greater than 0. Okay, and so we saw two examples here. We saw f of x equals x squared, uniformly continuous. Well, so this is just any e and r bounded. All right, so we saw this example, f of x equals x squared, on any bounded subset of the real numbers. We saw that that's a uniformly continuous function. And then the one we just saw is that f of x equals 1 over, that's a 1 over x on the interval a to infinity for a greater than 0. We saw that that also is an example of a uniformly continuous function. So both of these are examples of a particular class of functions. And these types of functions these two functions would fall into the class of functions called Lipschitz functions. They satisfy what we call a Lipschitz condition. Okay. All right. And so what is this condition that we see for these? Well, if you recall back, like in both cases, what we're using to establish the uniform continuity is some kind of a boundedness or some kind of a bounded quality, right? And so what is a Lipschitz function? Well, we say that a function f from E to R, and we say it satisfies a Lipschitz condition on E if there exists some constant, positive constant m, such that f of x minus f of y is less than or equal to m times x minus y for all x, y in E, right? And if you think about what the two examples we've seen, this is exactly how we establish the uniform continuity, right? And so all such functions, all functions that satisfy this Lipschitz condition, are naturally going to be uniformly continuous. Now, it turns out that not all uniformly continuous functions are Lipschitz functions, but the reverse is true. Lipschitz functions are always uniformly continuous. Okay. And so we can write the theorem stating that. We can write this theorem. Let E be a subset of real numbers and f a function from E to R. Now, if there exists an m greater than 0 such that f of x minus f of y is less than or equal to m times x minus y for all x, y, and E, then f is uniformly continuous. Okay, and so basically what we're saying is that if your function is a Lipschitz function, then it is uniformly continuous, right? And we saw several, and so we won't prove this theorem. We saw several examples of how this works, and I think it's relatively straightforward. To prove this. But we did say earlier that you may have you may be able to find examples of uniformly continuous functions that don't meet this criteria, right? And if that's the case, well, if a function f does not satisfy the Lipschitz condition on E, then really determining whether or not it's uniformly continuous on E is way more difficult, right? If you don't have this bounded quality of a function, it may still be uniformly continuous, but it is not straightforward determining as much, right? Whereas if a function has bounds like this, it is very, very often simple to show that it's uniformly continuous. But in the case when you don't have a Lipschitz condition, the following theorem is very helpful. This theorem here, and we won't prove this one either, I'll just state it. It's a very interesting theorem though. So if K is a subset of real numbers and is compact, so if K in R is compact and f is a function from K into the real numbers is continuous on K, then f is uniformly continuous on K. So if the domain set is compact, and f is at least continuous. If you know f is continuous and it's defined on a compact set, then this the function must be uniformly continuous. So if you have a compact set as your domain and your function is continuous, then in fact your function is uniformly continuous. So something about the domain set being a compact set implies that you not only have that you have uniform continuity if you have continuity. It's a special kind of continuity. Okay, and so some of this stuff will come up later. I'm not going to prove this theorem, but this is just an interesting connection between compact sets and uniform continuous functions, right? So wanted to point that out. Okay. And so that's where we'll end uniform continuity. And we have one more section here discussing continuity and functions, and then we will jump into derivatives. And so until then, take care.